Alright, so here is another video on solving these types of problems. Now, instead of working with a finite amount of potential vectors in Y, we're now going to work with infinitely many. They just have to take this form. And if you haven't seen it before, I have it in the notes that I'm posting with this, but this essentially means all the vectors y1, y2, such that this condition is met. And so the first thing I want you to notice is that p dot y is equal to p1 y1 plus p2 y2. And we assume p1 and p2 are positive because I don't know about you, but I've never seen prices that are $0 or negative. That would be pretty nice. So that means if we increase y2, the value of this whole equation is strictly going to increase. Why do I care about that? Well, we're subject to this constraint here. And so say I were to pick a value for y1, how about negative 9? And remember it's negative because it's an input in our netput vector. So that would mean y2 has to be less than 3, square root of negative 9. So y2 is less than or equal to, 3 times 3, so 9. Which means we have our vector here. We can pick anything less than or equal to 9. We could pick 0, we could pick 2, 5, or we could pick all the way up to 9. But as we've seen here, we always want to pick as high of y2 as possible as we can because we're only going to be making more money from it. So we're going to choose the highest possible, which is 9. Which means for finding the profit maximizing point, this is always going to be equal, because we always want the highest y2 we can get, subject to our constraint. That doesn't mean, though, that the definition of y changes, because we can still produce something that is less than optimal, like this, but it would always make more sense to instead produce this, if we can, which we can up here, so we're always going to do that. But we still could do this, so this is still an element of y. I want to make that distinction clear. So now for the purpose of solving, we're going to put this information up here to get p dot y is equal to p1 y1 plus p2 times 3 square root of negative y1, which we can rewrite as 3p2 root negative y1. So now what we're maximizing amounts to a single variable maximization problem, which you might remember from Calculus 1. And the way we solve these is setting our derivative equal to 0 and figuring out what has to be true about y1. Because if you have a continuous function like this, that's terribly drawn, in order to be at a maximum, the tangent line has to be 0, because it has to have a slope of 0. Because if it's not, you could keep progressing up the curve until you do hit a maximum. So we're going to set this derivative equal to 0. First, we solve for the derivative. And this ends up equaling p1 minus 3 over 2 p2, 1 over root negative y1. And now to set that equal to 0, means p1 equals 3 over 2 p2, 1 over root negative y1. We can move this to the other side, so we get root negative y1. We can move this to this other side. We can now square both sides and get rid of this piece. And now I want to point out that if you have something like this is just normal multiplication, you're doing this twice, and so it does not make this a positive sign. For example, the square root of negative 3 times the square root of negative 3, or I guess I'll do negative 3, square root of 3 times square root of 3. That's a terrible example. I'll do negative 4 in each of these to make it go easier. So that ends up being square root of 4 times square root of 4, which is equal to 2 times 2, which is 4. We can just get rid of these when we're squaring like that. And now, for example, if we got rid of the negative sign when we did this process, then we would end up with whatever. Anyway, I think I just went off on a tangent into nonsense, but that's okay. It's late here, so anywho, this is the algebra that we get. I've never been great at explaining algebra, so if you've made it this far in the video, sorry. So this is what we're left with. We can bring this negative sign over to the other side, and we get something like this. Now, it's entirely possible I've done some algebra wrong along here, but this looks roughly familiar to what I got in my notes earlier, so we're going to keep going. And now that we have our y1, we can come back up to our constraint, which is y2 equals 3 root negative y1. And I guess I'll say not our constraint, but the thing we figured out has to be true at an optimum. And we see y2 equals 3, the square root of negative 3 over 2, p2 over p1 squared. And that's how you solve for y2. So then you would take whatever you've gotten there, and that would be y star p1, p2 would be those two functions. Something like negative 3 over 2, p2 over p1 squared, and then whatever this piece is. I'm going to spare you guys the details of me struggling through computation, but that's the idea. And then similarly, the profit is just p dotted with our optimal y. And that all ends up working out to find profit and the optimal y. Hopefully that made a bit of sense. I'm now going to do a video showing you the geometry, and yeah.